This is going to be a quick overview on my machine learning model to predict the power output based off of various weather attributes such as the temperature and the relative humidity. So using the sample data we were provided, you can see I've sliced it into our training data, and over here we have our validation data, which we'll look at the end. And the first thing I did was just to do a quick analysis of the data and make sure there were no extreme outliers and nothing was null and we had nothing of concern. Given this was seeded data, this was not necessarily a needed step, but a useful tool for validation for a learning project. So once I had sliced off a piece of the data and I had a training set, I went into model test 1, which was very standard linear regression using Excel. And mostly what I was looking at this first run was my coefficient results. So we can see down here our temperature, our vacuum, our air pressure, and our humidity, how impactful they were to our model. The biggest thing that was standing out to me in this was the average temperature was such an outweighed impact compared to everything else. Given that our standard error and our adjusted R were looking relatively healthy for our target values, I just decided I wanted to investigate this a little bit more. So first thing I did for my model test 2 was to normalize the values. I didn't notice the pattern where the larger the value is, the smaller our coefficient is. So I just wanted to validate that that wasn't a symptom of the actual size of the values. So in model test 2, I did a normalization just to make sure that we were looking at equitable coefficients. And what we saw at the end was some small changes, but the overall trend was that our temperature was our single biggest predictor of our output target value over here. So since normalizing the data didn't really have a meaningful impact on the coefficients, I decided not to continue using it just because it added complexity to the actual algorithm. We wanted to leverage the model against the validation data. So for model test 3, the only real change I made on our linear regression model was to remove this AP normalized or AP air pressure entirely because it was so unimpactful to the end result. So if we look at model 3, we took a look at the difference between 3 and 1, and we saw that it was relatively in line. Not a massive change, but there was some meaningful change, especially on our standard error. So one experiment I wanted to run was to look at the residual outputs and actually plot if there were any of these variables that did not show a linear relationship individually. So the only one I have saved here is from our relative humidity because everything else showed a fairly linear relationship, but did notice that this was not showing a meaningful trend. So even though it had a relatively low coefficient, it did have a coefficient. I didn't want to eliminate it entirely. So for my model test 4, what I did was I decided to make it an interaction term with our temperature to see how it actually combined with temperature to change the model. So looking at model test 4, you'll see we have our new interaction term, temperature plus or temperature times humidity in addition to the temperature and humidity themselves. And again, not a massive swing, but considering we added a new variable, seeing this positive change in our R squared and adjusted R squared gave me confidence that I was at least moving in the right direction. The biggest change we saw in this model was actually a change in the coefficients though. We see down here our average temperature was, if we go back real quick, a 2.02, dropped all the way down to 1.3, and a similar distribution to our coefficients down here. So while this didn't have a massive swing in our accuracy or our standard error, I did feel it was important that we, to a degree, de-risked it because we reduced the weight of a single coefficient pretty significantly. So now if we had any huge changes in average temperature, it wouldn't necessarily send our prediction off into the stratosphere, basically. So with a model that I was feeling pretty strong, I didn't want to overfit the model, and I felt like fine-tuning this anymore was at risk of overfitting the model. I decided to run it against our validation data. Just to double check, I also ran our model 3 coefficients to see how we change. And here are the final results. of both models. We'll see that our model 4, again, it's not a huge swing, but our numbers do skew slightly higher, slightly better. Our standard error is down slightly, and with the reduced risk of our temperature swinging a stray sample, I felt strongly that this was a solid model to predict that got us to good accuracy, a solid standard error, and reduced complexity to the overall data. And that's how we ended our model example.